Our group did Internet of Things, and this presentation is by Sai, Josh, Jay, and Oscar. Myself. Next slide. Next slide. I will be talking about future trends in architecture. Before that, I would like to touch a bit about the evolution of the cellular network. The first generation came out in the early 1980s. This network was only used for voice calls, and the speed was quite slow, but for the standards of those years, it was pretty good. The data reached up to 2.4 kilobytes. And then 10 years after, the second generation network was introduced in the 1990s. Second gen introduced key features like SMS and also included some email services and increased the speed up to 64 kilobytes per second. The third gen was introduced in the 2000s and also implemented web browsing. Here, the data reached up to 2 megabytes per second and was quite a big jump from the previous generation. But where the real jump in speed came was from the fourth generation, which offered up to 100 megabytes per second and allowed some other applications like video conferences and online gaming. The fourth gen also introduced LTE, which stands for long-term evolution. We all know LTE. This is what allowed for the 100 megabytes per second. Next slide. Currently, we are just reaching this state of the fifth generation. It's brand new. Some countries don't even have the capabilities for it. So the fifth gen is looking to be 100 times faster than the fourth gen, which would be rates up to 10 gigabytes per second. A lot of new technologies have been coming out with this fifth gen, like smart vehicles, smart homes, and many other Internet of Things enabled devices. Most of the technology that will be using 5G hasn't even come out, so we will still have a few years to wait out. Next slide. Even though the fifth generation is just being explored and all that, they're still looking into the sixth generation, meaning the future of the network. The sixth gen is looking to be released in the early 2030s and expected to have some really phenomenal features, such as the 10 terabytes per second speed range. This is a massive improvement of data speed, and it will lead to a lot of technology like artificial intelligence onto wireless networks and cell-free networking. Some other applications will be robotic and autonomous systems, wireless brain computer interfaces, blockchain technologies that we're currently seeing, space travels, and much more. The main technology being considered to enable the future generation is massive MIMO. Next slide. MIMO, or known as multiple input, multiple output, has been used since the 1970s, but right now what we're doing to allow it for the future generation is using massive MIMO, which is a brand new technology. Massive MIMO involves using a lot more antennas than regular MIMO, which allows for more traffic per se, and expand the bandwidth for this type of network. I'm done.
I'm Jay, and I'm going to talk about security issues, lack of standardization in IoT devices. Lack of standardization in IoT devices makes them more difficult to manage, such as issues in privacy. Privacy can be intruded upon by the manufacturers and companies, and they are allowed to use the data in either ethical or unethical ways. Next slide. Some objects may have years and decades service of life, and examples of these would be medical devices that are implanted, electrical transformers connected to the electrical grid infrastructure. Security issues impacting security applications and monitoring of IoT devices. Some devices do not have robust capabilities. One of the main reasons IoT devices are wrong was because they lack computational capacity for built-in security. Even though some IoT devices lack robust computing capacity, they can still be infected by malware. Different devices with years of service may not be inspected and maintained at the same rate, and this lack of standard of IoT devices makes them much more difficult to manage on the IoT network. Next slide. Physical security issues. So physical security issues in IoT could be such as service technicians and their items that they use, proprietary items, could be tampered with or stolen unknowingly to the technician. Physical security includes the network perimeter level security like talked about in class, such as the stationary devices deployed at various locations. IoT devices that are not properly secured or monitored would allow a hacker to hack these points at different locations in the network. For example, accessing sensors and replacing them with the attacker's own equipment. An attacker might access the equipment and then this allows them to compromise the network. Next slide. In 2016, there was a large attack by malware by Myrid botnet, a botnet that infected many IoT devices and brought down many websites. The botnet was found to be running on devices like IP cameras and DVRs. The botnet is a distributed denial of service attack, or a DDoS. A DDoS attack is an attack that inundates the target with requests containing hundreds of thousands of devices, which slows the traffic to the target. In this case, a web server. The target becomes overwhelmed, and eventually the legitimate users are unable to get to the website and the server will crash. During this DDoS attack by the Myrid botnet, the host for such website as PayPal and Twitter was blocked. Next slide. Now, the attacker could also be in close proximity instead of stealing the hardware. And they could have access to insert their own malware or in that capacity. Some attacks could occur by an attacker being near vicinity of the object, such as sensors or medical devices. Sensors, which are in operation to take measurements or acquire data, individually may seem of limited use. However, with a network of sensors of a certain type, it may be useful in gathering data and allow the attacker to passively gain information on the network. IT professionals need to constantly be aware of this type of security, physical and otherwise, and it should not be overlooked. Hopefully, further research will help mitigate such security issues.
Next slide. I'm sorry, I'm talking about efficiency and performance in IoT. IoT has been well acclaimed for making processes more efficient in all spectrums. We have devices such as smart assistants, such as Alexa, Siri, Bixby, which have made daily query tasks easier, smart lock systems such as Ring, which have made home security easier, and even smart refrigerators, which make grocery list making easier. With these devices making everyday life easier, more and more people are investing in these devices, bringing some concerns to light. Next slide. One large concern with the rapid increase of IoT devices is scalability. Take this quote. In 2011, there were approximately around 12.5 billion devices. Now by 2020, there are around 50 billion devices, a difference of 37.5 billion devices in just 9 years. Within this time, computational power has also increased, with computer chips becoming more powerful and faster. This allows more devices to join the IoT network than ever before, and this trend shows no signs of slowing down. The main issue with the scalability becomes how fast and efficient can we develop the network to handle this new traffic? Next slide. Bandwidth. This is a big concern with scalability. Think of bandwidth as the number of lanes in a highway. When there are too many cars at any one given time, we get traffic jams. For IoT, this issue becomes issues with network delays and receiving information from requests sent out from devices. Engineers are trying to tackle this issue in two ways, using data structures and algorithms and through data storage options. Next slide. Data structures and algorithms. The data structure that is most synonymously used with any network similar to the IoT is a graph. A graph consists of edges and vertices, which are also called nodes at times. The problem we have to solve is how to reduce the amount of time required for data to transport between one node and another node. Next slide. The idea behind network coding, which is one solution proposed to network delays, is to utilize graph theory and to create a new algorithm for efficiently retrieving data. To do this, we associate nodes, or the circles in the graph, with processing units that receive encoded information and then send out encoded packets to other nodes until the destination node is reached, sort of like a game of pass the password. This approach is in contention with the traditional approach of store and forward paradigm, where this encoding is not done. This is less efficient, but this network coding makes the process more efficient. Next slide. Data storage is also an option which has been looked into as a solution for scalability issues. With device numbers rising, there's a constant need to store massive amounts of data. Each device needs to store data for accounts, preferences, and for functions it needs to do. Even more important is to be able to retrieve this data in not seconds, but milliseconds. This is where cloud storage comes into play. Next slide. In-house cloud storage is useful and cost-effective to a limited extent, but is also very expensive to scale. This is where we have host companies where the main point of using these specialized vendors is to pass on the burden and the cost of maintenance and storage to these host companies. This cloud storage option affords companies virtually unlimited scalability for storage, solving our current scalability concern for data storage for now. Next slide.
What does the IoT development cycle look like? The current system has multiple phases, such as software development, hardware development, cloud integration, testing, manufacturing, marketing, and deployment. During the software development portion of the project, the algorithms need to be decided for the device to be functional, and they should be written. Most of it should be done in a light language such as C or Python to minimize stress on the device, as these devices carry weak hardware. During the hardware portion of the development cycle, developers are looking to make a clear circuit diagram, decide which components make the most sense for the device, select the onboard controllers, and decide how and which intended actuators will affect the device. During the testing phase of development, testers will be used to check, inform, and critique how well the software and hardware integration with each other works. After testers have confirmed the product to be functioning at the level that will meet the end user expectations, the product can now be fully integrated into the cloud environment. Using a large cloud computing platform such as ThinkSpeak, that data that is being collected from the device can be efficiently farmed and analyzed. Once all this is completed, now begins the app development process. The goal is to make a simple interface to allow users to easily control and monitor their devices. This phase of the development process is usually the least time and effort consumed because either A, a vision for the app should have already occurred before development, or the application is not like an integral part of the device. During the deployment phase of the development cycle, packaging containers will be designed for safety and security purposes, putting on common additions to the box such as logos, package information, etc. With this proposed development cycle, it's clear for businesses and developers how and what it takes to develop a tangible IoT product. To build these IoT devices, you require hardware developers with advanced skills in soldering, identifying all the components, including the sensors, microcontrollers, positioning the circuit board. Software developers have extensive experience working with languages like C and Python. Cloud infrastructure engineers that can efficiently integrate all of your hardware with the cloud. App developers for multiple platforms. Testers that have light skills in essentially every single phase of the development process. Deployment engineers that are skilled enough to transport all of the constructed devices in the safest and most efficient way. And lastly, the marketing managers to help promote the product to as many people as possible. The current issue with IoT development. The development cycle for IoT devices is a long and arduous process for most businesses because of the sheer manpower that is required in all of these different stages. Lack of maturity for these devices make it difficult for marketing managers to get these products in the hands of consumers, along with the plethora of software vulnerabilities. At the start of this wave of technology, the availability of experts is very limited, and the upfront cost made it unfeasible, causing most IoT products to fail. IoT requires a plethora of experience that most companies don't have readily available. Not only does this make it expensive to build, but also expensive to maintain, even with cloud services. To have a useful IoT product, a company needs to aggregate and analyze the backend data constantly. And the manpower to do that is just not available. Many IoT devices run low quality software due to their weak processors, and these devices have known to have vulnerabilities that were more commonly susceptible. Computers were more commonly susceptible to in the late 90s and early 2000s. That just goes to show how far back we are in terms of security for these IoT devices.